Swayam Prabha. Digital India. Educated India.
So, welcome to our continuing series of lectures on transport phenomena, where we had looked at how to do shell balances for specific problems which had specific symmetries. For example, in the flow past of the heat transfer and mass transfer from a flat surface where it was infinite, therefore, there was only transfer in one direction. Similarly, in a cylindrical geometry, we looked at transport only in the radial direction. In general problems, there is transport in all three directions simultaneously. So, there is a variation of concentration in all three directions, and there is a variation of concentration in time as well. In that case, we can derive general conservation equations in all three directions as well as in time, which are general, so that they depend only upon the specific coordinate system that are being used. And then for specific problems, we can simplify these equations and then use them. Okay. So, in that spirit, we had started deriving balance equations in the previous lecture. We had looked at a Cartesian coordinate system, where the surfaces are the planes are surfaces of constant coordinate. Okay. In this case, you have to take a differential volume whose surfaces are surfaces of constant coordinate, and then write a balance equation for that differential volume. And I had shown you how we do it in this case. We took a cuboidal volume of volume delta x, delta y, delta z in the three directions, and wrote a balance which basically stated that change in mass is equal to mass in minus mass out plus any accumulation. The change in mass in time delta t was just equal to the change in concentration times the volume itself. Now, the mass in and the mass out of the surfaces of this differential volume, there are 6 surfaces, the left and the right, the front and the rear, and the top and the bottom. Mass in and mass out could be for two reasons. One is due to convection and the other is due to diffusion. The convective flux is just the normal velocity times the concentration, because it is only the normal component of the velocity that is changing the mass within this differential volume. So, the flux is the normal velocity times the concentration for convection, and for diffusion it is just the diffusive flux. Okay. And on the left surface at x minus delta x by 2, when the velocity is positive or the flux is positive, mass comes in. So, therefore, the mass in was written as the convective flux times the surface area, perpendicular surface area, delta y, delta x times delta z times time at that surface, plus the diffusive flux times the surface area times the time interval. That was at the left surface, where the mass within the volume increases if the flux is positive. On the right surface, the mass within the volume decreases if the flux is positive. Okay. Therefore, that constitutes a mass leaving the surface. That mass, convection once again, is uy times c, that is the flux times the surface area and time, and diffusion is jy times the surface area times time. Okay. And similarly, we had calculated fluxes from the front and the rear surfaces, which are perpendicular to the x axis. Okay. So, they are separated by a distance delta x, and the top and the bottom surfaces which are perpendicular to the z axis, and they are separated by a distance delta z. Okay. Once we had these, we had put all these together, okay, to get the balance equation. Okay, which included the sources in general, and then you divide throughout by the volume, divide throughout by time, to get the difference equation, which is the next equation here, okay, and then take the limit of delta t going to 0 and delta z going to 0, volume going to 0 and delta t going to 0 to get the differential equation. Okay. I had expanded out the differential equation for you and written it in a slightly different form. Okay. I had written this in a slightly different form, and then I had substituted the constitutive relation, okay, in this case Fick's law for diffusion. The flux in the x direction is related to the velocity gradient in the x direction. Flux in the y direction is related to the velocity gradient in the y direction, and similarly for the z direction. And you can substitute these in and get an equation of this form, which has on the left side, okay, the time derivative and the convection terms, which are first order derivatives in the spatial locations. On the right side is the diffusive term, which is a second order derivative. Okay. These equations can be written in a slightly more compact form. Okay. For that, let me go back and draw a coordinate system once again. Okay. This is x, y and z. Okay. The velocity is actually a vector. Okay. It can be written as the sum of the components times the unit vector. Okay. The unit vectors, I will use the symbols Ex, Ey and Ez, okay, for the unit vectors rather than ijk or some other symbols that you are familiar with. This notation makes it clear what exactly I am referring to. Okay. Okay. And I will use the underline to represent a vector. Okay. I will use the underline rather than using an arrow on top to represent the vector. Okay. So, this is the velocity vector. Okay. There are 3 components and there are 3 unit vectors. Okay. Now, the flux that I had here also has 3 components. Okay. The flux also has 3 components. So, the flux can also be written as a vector. Okay. I can write j vector is equal to jx Ex plus jy Ey plus jz Ez. And you know what jx, jy and jz are. Okay. So, this is equal to minus d partial c by partial x Ex minus d partial c by partial y okay. So, that is the expression for the flux. Okay. So, I can write the flux also as a vector. Okay. The flux has a direction. Okay. There is a particular direction in which that mass transport is taking place. Okay. Just as the velocity is a vector at some point in the flow, okay, it could have some particular position. The flux is also a vector. Okay. At any location, okay, it could be in one particular direction. I can resolve that vector into the fluxes along the x, y and the z directions. Okay. The component of that is jx, jy and jz. Okay. And if I add up jx times that unit vector plus jy times that unit vector plus jz times the unit vector Ez, I get a vector flux. Okay. That is the resultant of these 3 fluxes. Okay. It is the resultant of these 3 fluxes, the vector addition of these 3 fluxes. Okay. So, I can also represent the flux as a vector. Okay. Now, you can see that in this, okay, I have dc by dx times Ex, dc by dy times Ey and dc by dz times Ez. Okay. That is acting on the concentration field. Okay. So, this I can write it as minus d times Ex d by dx plus Ey times C, okay, where this thing is now a vector in itself. Okay. It is a differential operator, but it is a vector differential operator. Okay. So, if I take dC by dx at a given location, okay, at a given location the concentration field will vary in all three directions. Okay. I can take the variation in the x direction dC by dx, variation in the y direction dC by dy, variation in the z direction dC by dz, okay, and then I can add these three after multiplying them with the unit vectors to get a resultant vector. Okay. So, this thing is a resultant vector, okay, of the concentration variations in the three directions. Okay. This is a resultant vector of the concentration variation in the three directions. Okay. You can define this vector. Okay. It is usually written by the gradient symbol. Okay. Grad is equal to Ex times partial by partial x plus Ey times partial by partial y. Okay. And if I define it this way, I can simply write the flux, okay, as minus d gradient of the concentration. So, that is how I would write the flux in terms of a vector derivative of the concentration field. Okay. So, let us go back and look. Okay. We have defined the velocity field as Ex Ux plus Ey Uy plus Ez Uz. Okay. Defined the flux as Ex Jx plus Ey and I have defined a vector derivative, a vector spatial derivative as del is equal to Ex partial by partial x plus so, these are the three operators I have defined. Okay. Now, this will help me write the equation much more compactly. Okay. So, the first thing, okay, the flux J vector, okay, is equal to minus d, okay, into Ex partial c by partial x plus Ey partial c by partial y plus Ez partial c by partial z. Okay. This I had written as minus d times the gradient of the concentration. Concentration is the scalar, that gradient operator is a vector. So, I get a flux that is a vector. Okay. Now, let us go back to the conservation equation. Okay. The conservation equation that I had was dC by dt is equal to, I am sorry, now these terms here, okay, I can write them as, okay, Ex d by dx plus Ey d by dy plus Ez d by dz, okay, dotted with Ux, okay, look at this expression. Okay. When you take the dot product of two vectors, you have to multiply their components and dot the unit vectors. Okay, you have to multiply the components and dot the unit vectors. Okay. So, if you take for example the first term in this expansion, which consists of taking the dot product of these two, what you get is E x d by dx of u x, I am sorry, u x E x. Okay. And there is a dot product, you have to multiply the components and dot the vectors. In this particular case, the unit vector E x is independent of position. Okay. If you recall, in a Cartesian coordinate system, x, y and z, the unit vectors do not change with position. Okay. E x, E y, E z. Okay. They are the same regardless of what the position is. Okay. That is not true in curvilinear coordinate systems, as we shall see a little later. In the Cartesian coordinate system, the unit vectors are independent of position. So, I can take the unit vector out of the differentiation. Okay. So, I will get E x dot E x d by dx of c u x, okay, just equal to d by dx of c u x, because a unit vector dotted with itself gives you 1. Let us take the second term in the series, when this operator acts on the second term here. Okay. I get E x times d by dx of c u y E y. Okay. Once again, unit vector is independent of position. So, I get E x dot E y d by dx of c u y. Okay. And E x dot E y is equal to 0 because they are perpendicular to each other. So, this term becomes 0. Okay. Similarly, this first term acting on the third term here will also give you 0. Okay. So, only the components that are acting on the same in the same direction, for example, the gradient of the u x velocity times concentration, the derivative with respect to y of u y times the concentration and so on, those are the only terms that will remain. Okay. And therefore, this equation will reduce to this equation that I had here. Okay. So, if I take the dot product, okay, of this dot product is just dot product of del dot u c. Okay. So, this first term is the gradient operator dotted with the concentration times the velocity. Okay. Therefore, this second term in the equation can effectively be written as partial c by partial t plus del dot u c. Okay. This is called the divergence. The dot product of the gradient operator with a vector is called the divergence of that vector. Okay. Similarly, the term on the right can be written as E x d by dx dotted with j x same argument. When you take the dot product, E x dot E x is 1, E x dot E y and E x dot E z are both 0. Okay. So, therefore, this will just give you del dot j vector. Okay. And of course, there is a negative sign here. Okay, there is a negative sign here. Therefore, on the right side, I will have minus del dot j. And as you can see, this is an extremely compact form of writing the same equation, provided that I define the del dot operator as E x d by dx plus E y d by dy plus E z d by dz. Okay. And then I have j is minus d grad c. Okay. So, if I substitute this, I will get minus del dot minus d grad c. Okay. Note that the dot product is now between these two gradient operators. Okay. The dot product is between these two gradient operators. If d is independent of position, this just becomes equal to d del square c, okay, where this del square is del dot del, okay, is equal to E x dotted with itself. And once again you can see that E x dot E x is 1, E x dot E y is 0. Therefore, only the terms which involve derivatives of the same coordinate will be multiplied by 1. Derivatives of two coordinates will be multiplied by 0. Okay. And therefore, this just gives me d square by dx square. Let me write this somewhere else. Okay. Okay. So, this will be equal to d square by dx square plus d square by dy square plus d square by dz square. Okay, it contains the second derivatives with respect to x, y and z. Okay. So, in this vector notation, my differential equation has taken the form partial c by partial t plus del dot u c is equal to d del square c, okay, where this del dot u c on the left side is partial by partial x of u x c plus partial by partial y of u y c plus partial z of u z c. Okay. And on the right side I have, okay, d into d square c by dx square okay. This is called the Laplacian. Okay. This operator is called the Laplacian. Okay. And this thing here, the del dot of a vector is called the divergence of that vector. So, this is the general form of the conservation equation. This form, so this is general, this is general. Okay. The interpretation of the divergence, the explicit expressions for the divergence of the Laplacian will depend upon the coordinate system. In this particular case, when I took del dot del, there was a derivative acting on the unit vectors, but that was 0 because in the Cartesian coordinate system the unit vectors are independent of position. That is not in general true in other coordinate systems. So, therefore, the forms of the Laplacian and the divergence, okay, that is del dot is equal to E x sorry. These forms will change when you go to another coordinate system. Okay. However, this equation does not change. Okay. The general equation that you have dc by dt plus the divergence of u times c on the left side and a diffusion coefficient times the Laplacian of c on the right side, that does not change. Okay. That is the same for all coordinate systems when written in this vector form. However, these things will change. So, in the next lecture I will derive for you the conservation equations in a spherical coordinate system. X, y, z was the Cartesian coordinate that we were using. When you have a spherical geometry, you would expect a coordinate in which the surface is a surface of constant coordinate. That is a spherical coordinate system in which one of the coordinates is just the distance from the center, r. One of the coordinates is just the distance r from the center, from the origin. However, you need two other coordinates to completely specify a location. In the Cartesian coordinate system, we had x, y and z to completely specify. In this case, r is just a distance from the center. You need two other coordinates to completely specify a point in this spherical coordinate system. And those two coordinates are actually the angles made by this radius vector with the coordinate axis. One of these is what is called the azimuthal angle theta, which is the angle made by the radius vector with the plus z axis. And the second one is what is called the meridional angle, phi. If I take a projection of r onto the xy plane, if I take a projection of r onto the xy plane and I calculate what is the angle that this makes with the x axis, that is what is called the meridional angle phi. So, you can easily see that this z is basically equal to r times cos theta. This height is r times cos theta because theta is the angle made with the z axis. This projection is equal to r sin theta. So, therefore, I have z is equal to r cos theta. The projection along the xy plane, the projection along the xy plane is basically root of x square plus y square. That is the projection, that is the length of this line of the projection along the xy plane, that is equal to r sin theta. And this makes an angle phi with the x axis. Therefore, x will be equal to r sin theta cos phi, y will be equal to r sin theta sin phi. So, there is a conversion from the spherical coordinate system to the Cartesian coordinate system. The radius is just equal to square root of x square plus y square plus z square. Distance from the origin is the radius. Now, theta is the angle from the plus z axis. Therefore, theta can vary only from 0 to pi. Theta is the angle from the plus z axis. When theta is equal to pi, you reach the minus z axis. When theta is equal to pi, you reach the minus z axis and you cannot go any further. Therefore, theta has to be between 0 and pi. Because theta is equal to pi is the minus z axis. Once you have reached the minus z axis, that is the maximum you can go. You cannot go any further. Phi on the other hand is the angle around the z axis. Phi is the angle around the z axis, the angle made with the x plane around the z axis. So, therefore, phi can go from 0 to 2 pi. This spherical coordinate system is something that most of you would have seen in the past. That is what is used, for example, for defining the latitudes and the longitudes on the globe, on the earth. The z axis is the north south axis from the two poles. So, that is the z axis. The equator, we write it as a 0 latitude, okay. That is because we take the latitudes to be 0 at the equator, and it goes to plus 90 at the north pole and minus 90 at the south pole, okay. The northern latitude and the southern latitude. In the spherical coordinate system, okay, this north pole would correspond to theta equal to 0, okay. I take theta from the plus z axis, therefore, the north pole would correspond to theta equals 0. It would increase, theta will be 90 at the equator and then 180 at the south pole, and it cannot go any further, okay, because the south pole is on the minus z axis. So, that is theta, okay. Whereas conventionally on the globe, theta, the latitude is 0 at the equator. When expressed in terms of theta, it is equal to 0 at the north pole and it goes to 180, okay, rather than going from 0 to plus 90 and 0 to minus 90, okay. And phi is the meridional direction, okay, and phi goes from 0 to 360 all the way around the globe. That is the angle phi here. In the globe, this is measured from the 0 meridian is at Greenwich in England. It passes through there. You can choose any arbitrary reference for the meridian. It goes from 0 to 360. So, these are the angles theta and phi in this spherical coordinate system. In the next lecture, I will construct a differential volume in this spherical coordinate system and write a balance for this differential volume. As I said before, in the differential volume, the coordinates, the surfaces have to be surfaces of constant coordinate. That means that in this case, the surfaces have to be surfaces of constant theta, constant r and constant phi, rather than constant x, y and z as we had in a Cartesian coordinate system. So, we will construct those surfaces and then write a flux balance for those surfaces in the next lecture, okay. And then we will derive the conservation equation in a spherical coordinate system, and I will try to explain to you how that is different from a spherical coordinate system, but when written in vector form, the equations are exactly the same. So, we will continue this derivation of a spherical coordinate system in the next lecture. We will see you then.